The P versus NP problem has been around for quite some time, for decades, as a matter of fact, and it's such an important problem with so many fascinating implications that it's a problem a lot of people have looked at, and yet I think from a scientific perspective, from an academic perspective, we have barely scratched the surface. We're really the very tip of the iceberg in terms of being able to attack this problem and come even close, or even remotely close to a solution for the problem. And one of the biggest advances, I think, in the last 30 years in terms of being able to take the P versus NP problem and come up with something that can help us really tackle it comes up in this notion of NP complete problems that I introduced in the previous video. Okay, and what I want to do in this video is talk a bit about what it would take to prove something around the P versus NP problem. What would it take to prove that either that the P and NP are the same, or what would it take to prove that they're different? Okay, and a lot of that will come into being able to reason about or being able to get more insight into these NP complete problems. Okay, so first of all, if you wanted to, let's say, prove that the P equals NP, okay, it turns out that all you would have to do, and all being a very relative term here because it's not easy to do, is you'd have to come up with a polynomial time algorithm, a polytime algorithm, or an efficient algorithm for being able to solve a NP-complete problem. So for example, if you came up with a polynomial time algorithm for being able to solve a problem like clique, that would be sufficient for being able to show that P is equal to NP. Alternatively, maybe if you find a way to solve traveling salesman efficiently, or you find a way to solve the Sudoku problem, and when I say Sudoku, I mean generalized to an n by n grid, as opposed to maybe a 9 by 9 grid, etc. These are all ways in which you could solve the P versus NP problem. Okay, and it's amazing because even though these problems are important, and even though these problems have been around for quite some time, uh, no one's really made progress in being able to solve any of these problems. Okay, now actually one thing that's particularly interesting is given the popularity, the fame of the P versus NP problem, you can imagine a lot of folks have tried to work on it, and of all the people that have worked on it, not all of them have a very rigorous mathematical background. So over the years, there have been many flawed proofs of the P versus NP problem, and I've actually seen a number of these flawed attempts. And one of the most common flawed attempts to solve the P versus NP problem happens when someone proposes what they think is a new polynomial time algorithm, a new efficient algorithm for solving one of these NP-complete problems. And where these approaches actually fail, what I've typically seen, and what I think makes this particular problem so hard, and what makes it so hard to come up with an algorithm and really pull this whole approach off, is that the algorithm actually has to be correct on all inputs, okay? Even if you could solve, I don't know, traveling salesman on 99.9% of input instances, as long as there are some hard instances out there that cannot be handled by the algorithm, that's enough to say that the P versus NP problem has not been laid to bed. It hasn't been put to rest yet. Okay? Now, what I do also want to say is that maybe this is a more subtle technical point, is that technically speaking, you don't actually have to actually come up with a polynomial time algorithm for solving an NP-complete problem to prove that P is equal to NP. You just have to show that one exists. Okay? And in other words, your proof does not have to be constructive, and constructive proofs are proofs where you actually would produce an algorithm, but it's entirely possible you can come up with a non-constructive proof, a proof that shows an algorithm must exist without actually showing what the algorithm is. And I think that's a little less likely to happen in this case, but there are mathematical proofs of that nature. So I just want to point out that that is one possible angle with which you can attack a problem like P versus NP. Now, having said all this, I would personally be shocked. I would be surprised if somebody came out and proved that P is equal to NP. In fact, I suspect, as I think most theoretical computer scientists do, that P and NP are quite different. Okay, and there are a couple of reasons why I think that we're unlikely to show that P is equal to NP, and these are not very rigorous reasons. I mean, they are, but they are somewhat practical. So first of all, as I mentioned, there are a ton of NP-complete problems out there, problems that are universal in nature, problems that are thought of as the forefront, the hardest problems in NP, problems that if you solve any one of those problems, it would lead to a solution to the P versus NP problem. And it turns out that with all these different NP-complete problems out there, problems that are in very different domains, that are in a heterogeneous array of problem domains, there are a lot of smart people who have tried to come up with efficient solutions to one of these problems, but they have failed over the years. And so that would indicate, at the very least, that these problems are hard to solve, that there is no, that they're unlikely to have an efficient algorithm because somebody would have come up with something by now. I know it's not a strong reason, but it's just one reason to be aware of. Okay, and that's one aspect of why I think P and NP are not the same. Okay, now what's interesting is, and I think what makes this problem so intriguing is that there are so many domains and so many different problem types that are NP complete. Okay, finding a solution to any one of them would be sufficient. Alternatively, being able to show that any one of them cannot be solved efficiently would also do the trick, because these are problems that, if anything, these are the problems you would expect not to be solved efficiently because they are sort of the hardest problems in NP. And I think it's in this latter part where our best hopes lie of being able to resolve the P versus NP problem, because intuitively it seems like there's this fundamental distinction between coming up with an answer yourself versus verifying an answer that someone else told you. Okay, now most theoretical computer scientists feel that P and NP are not equal. Okay, and despite that sense that they are unequal, despite that feeling, neither I nor anyone else in the world, for that matter, currently can construct a logical argument, a mathematical proof to that effect. Okay, if you wanted to prove that P and NP were indeed different, one way to do so would be to simply come up with a problem in NP, and again, simply being subjective here, would be to come up with a problem in NP and then show that no matter what you do, that problem cannot be solved in polynomial time. Okay, and this approach, again, it's challenging since algorithms, and maybe at a more fundamental or maybe more philosophical level, the human beings who design them can be very clever. Okay, it's really hard to show that no matter what strategy you come up with, there isn't a better one out there that will show that P and NP are different. Okay, it's hard to show that no strategy will work. Okay, that no clever enough strategy will work to solve the problem more efficiently. Okay, and I think in a way, again, this is kind of talking about the philosophical implications. If you think about it, I mean, human ingenuity can show no bound in so many different regards. I mean, who's to say that even if a problem can't be solved today, who's to say that in 6 months or even 6 years from now, someone might potentially come up with a clever solution? Who's to say that that won't happen? And to prove that P and NP are different, you would have to effectively prove that no matter how clever the approach, it just won't work. Okay, you'd have to basically demonstrate that this kind of unconditional limit to human ingenuity for all these very interesting problems. And that, again, just seems like a very hard thing to do. It seems really hard to prove something like that. Okay? The last thing I want to do in this video, and probably in this video series, is talk a little bit about what would it, is there any recourse, even if P and NP are found to be different, okay, which we currently believe to be the case, that would imply that all these problems that are interesting cannot be solved efficiently. Okay, even if none of these problems had efficient solutions, okay, it turns out that even in that case, not everything would be lost. And I want to talk a little bit about why that is the case. And I think that it's important to note, first of all, that the P versus NP problem is a problem about worst case scenarios. In general, NP completeness deals with worst case scenarios. And it means that, there may be a lot of real world scenarios, okay, very many practical problems that you can solve efficiently. For example, Facebook, as I mentioned earlier, Google Plus and others, they might be interested in computing cliques on graphs, identifying subsets of nodes in a particular graph where each pair of nodes is connected to each other by an edge. Okay? And while in general, no one knows how to compute cliques efficiently on a general graph, it may be that in practice, the kinds of graphs that Facebook or Google Plus encounters, these social networking graphs, these graphs may have specific properties that may make it easy to find a clique. These graphs are not some arbitrary, crazy concoction. They may have other structural properties that are not so generic that make it within the realm of possibility that for that particular class of graphs, cliques can be found efficiently. Okay, so there may be the reality that maybe the worst case scenario never happens in practice, and all the typical scenarios you see in practice do not fall into this worst case category. Maybe they can be handled more efficiently. Okay? The second thing I want to point out, and this is on a related note, is that many times, and for many practical problems, you may be okay with an answer that's good enough, if not perfect. Okay, in other words, you may not need an algorithm that is exact. Maybe you can get away with an approximation algorithm. Okay, for example, maybe let's say you're given a graph and you want to know, is there a clique of size k? Maybe I can come up with an algorithm that, or maybe you are trying to find a clique of size k in the graph. Maybe I can come up with an algorithm that finds, some clique of a different size that's not too far from k. And actually, clique is a bad example because it turns out for clique in particular, it's actually hard to find even good approximations. But there are other algorithms, or other problems rather, that are NP complete, for which it turns out you can come up with more efficient, or you can come up with good approximations. And actually, traveling salesman is an example of a problem in this domain. It turns out that you can come up with some pretty good approximations, even if you can't come up with a perfect route that optimizes the cost. You can often come up with routes that are within a constant factor of the best or the most optimal solution. Okay, so there are many situations in which an approximation algorithm is good enough. So even if P and NP were different, life would go on, and there are various aspects of recourse that you can take solace in. Okay, so I think that's really what I wanted to say about the P versus NP problem. In general, hopefully over the course of this video series, you realize that this is a very fascinating problem. It's an open problem. There's just so much we don't understand about why certain interesting problems in mathematics and computer science and biology and so on, for some reason, many of these problems seem to be hard to solve. We have some intuition around why they might be hard, but we don't have any rigorous mathematical proof that shows that these problems are hard to solve, and that they will never be solved efficiently, no matter how clever a strategy we come up with for addressing them. And likewise, we don't know any efficient solutions to any of these problems. So hopefully over the course of this series, you gain an appreciation for the P versus NP problem. And I definitely would encourage you to look up some additional resources online. There's a ton of stuff available where you can get a better handle on the problem, get maybe more of a formal definition of P and NP. And if you are interested, hopefully you can try to tackle this problem and perhaps one day come up with a solution for it.